Okay, everyone. So here we're looking at the ionization of water. So what happens with water when it is with other waters? In a beaker, test tube, container, even in your a glass or a mug, water tends to, of course, attract other waters because it has hydrogen bonding and dipole-dipole and all of the intermolecular forces that you've learned about before. But because water technically behaves like an acid and a base, when they come in contact with each other, that's exactly what ends up happening. One of the waters will end up losing a proton or the hydrogen ion, and the other water that happens to collide with it will will accept that hydrogen ion. So this is referred to as the auto-ionization or the ionization of water. So as a result from that, we do have an equilibrium process, and the products here are hydronium and hydroxide. So actually any pure water, I don't want to say solution, but technically it is a solution now because it does have ions present. Now, keep in mind the percentage of product that is present is incredibly, incredibly low. So when we are referring to, a weak acid in solution or a weak base in solution, the amount of hydronium and hydroxide coming from water is not super impactful. And you'll see what we mean by that a little bit later on. So let's say we wanted to create a K expression here. So K expressions, of course, are always products over reactants. So in this case, if we wanted to set up a K for this, our products are ions, but our reactants are not, right? They're in their liquid form. So what ends up happening here is we have an expression that is hydronium times hydroxide essentially over 1, because remember water is not included. So this is referred to as Kw. Have you seen enough Ks yet? We have Keq, Ksp, Ka, Kb, and now we have Kw. So Kw is in reference to really the ion product constant, but more specifically, the water ionization constant. So you're looking at the hydronium and hydroxide coming from when we have a water, I don't want to say solution, but when we have water, when we're dealing with water. So here is where things are going to get interesting. This relationship is very important to make note of. As we continue forward and we take a look at changes that happen in hydronium and hydroxide concentrations, this relationship will be key. Okay, so just like any other K values are temperature dependent. But we do know that at 25 degrees Celsius, or essentially ambient temperature, the Kw for water is 1.00 times 10 to the negative 14. Now remember that that is equal to hydronium times hydroxide, right? That's our Kw. So this relationship will become important because if we know that we have a solution that's happening at 25 degrees Celsius, we can use this relationship to figure out one of our unknown concentrations. So, here, for example, it's showing you, well, how can we figure out what the concentration is of hydronium and hydroxide for just simply water? So if we set up our Kw expression and we use X to represent our ions, right? Almost identical to what we did when we did Ksp expressions, we end up getting Kw is equal to X squared, right? So if we square root both sides, we end up getting that X is equal to 1.00 times 10 to the negative 7. Now you probably don't wonder, why is this going to end up becoming important? Well, this relationship and this information about the concentration levels of pure water is really what the basis is for the, oh wow, I don't know why I did that, pH and pOH scale that we're going to look into more depth tomorrow or in the next section of chapter 5. So you'll see what I mean. But essentially, this relationship is important. Pure water concentrations is really the baseline for our pH being equivalent to 7 as being our neutral mark. And then the varying changes in concentration will indicate what the changes are in our pH. So here we have an increase in hydronium causes a decrease in hydroxide and vice versa. So what does that mean? Your Kw is equal to hydronium times hydroxide. So what happens is, for this value to stay constant, for Kw to be whatever it is at 25 degrees Celsius, and this is assuming temperature is not changing, what ends up happening here is once you have the value of 1 going up, the other will have to go down for this to be the same value for the Kw. So for it to stay at 1.0 times 10 to the negative 14, if your hydronium goes up, your hydroxide goes down, or vice versa. So both hydronium and hydroxide will exist in all aqueous solutions now. And the reason why we know that is because pure water in itself contains those ions, obviously in specific amounts. So if you have an increase in the amount of hydronium present, that will indicate that you have a pH below 7, which means that this solution is now acidic. If you have equivalent amounts, that's exactly what pure water is, which is what we saw, right? This 1.0 times 10 to the negative 7, then you have a neutral solution, of course. And if you have hydroxide concentrations that are now higher than hydronium, you're going to have a basic solution, which means your pH will end up being higher than 7. So in other words, depending on which one you have more of will indicate if you have an acid or a base. So if you have more hydronium, you're going to have an acid, and if you have more hydroxide, you're going to have a base. If you have exactly equivalent amounts, you're going to have a neutral solution. So let's take a look at some practice problems. So our first one here says, first make note, it says assume the temperature is going to be 25 degrees in each of these cases. Okay, so that's obviously important because we wouldn't be able to use our 1.0 times 10 to the negative 14 for our Kw. So it's asking us to calculate the hydronium and hydroxide concentration in a 0.15 mole per liter of perchloric acid. So we have to justify or prove why this solution is acidic. So of course we know this is going to be acidic. This is a strong acid, right? So perchloric acid is one of our strong acids. So let's write out the process of what exactly is happening here, just to kind of refresh our memories of what happens when this acid is in water. Ooh, I almost did the equilibrium symbol, but we know this is not an equilibrium. Drama. So we're going to have hydronium produced, and of course we're going to have our perchlorate ion. Okay, so they're giving us the concentration of this HClO4, right? So the concentration here is 0.15 moles per liter. Now, because this is, and I think I did mention this in today's lesson, because this is a strong acid, really we're just using stoichiometry mole ratios to determine the concentration of hydronium in this case. Because it's a 1-to-1 ratio, for every one perchloric acid molecule, you're going to have one hydronium that is produced. So the concentration is the same. So in order to justify that this is going to be acidic, we have to basically prove, we want to prove that hydronium ions are higher in concentration than hydroxide, right? So let's calculate hydroxide to prove this. So Kw is equal to hydronium times hydroxide, 1.0 times 10 to the negative 14, because we can assume, since they said it was 25 degrees, we have 0.15 moles per liter, and then I'm just going to put X in for our hydroxide. So our X value, which is our hydroxide concentration, is equal to 6.7 times 10 to the negative 14 moles per liter, which of course is less than 0.15 moles per liter that the hydronium was equivalent to. Okay, now this expression really can be used for any time you're dealing with an aqueous solution. Why? Aqueous solutions are automatically going to have water there. Of course, the concentration of hydronium and hydroxide is going to change depending on if there's anything present. But remember, this 1.0 times 10 to the negative 14 is only at 25 degrees. If it is any other temperature, they'll either have to give you the Kw or enough information that you could solve for it. All right, if you had the ions, you could solve for your K value. Okay, so calculate the hydronium and hydroxide in a saturated solution of magnesium hydroxide. So magnesium hydroxide is in fact a strong base because it's a group 2 metal with hydroxide, but it also happens to have a Ksp value, right? So because we're dealing with, the key there is the term saturated solution. So that means really we have our dissociation. We kind of have to do two things here. We have to use our Ksp equilibrium to determine the concentration of this molecule. And then we can determine the ions for hydronium, right? So it's kind of, we're combining our worlds here. Okay, so our Ksp is, and there's a train going by, which is amazing. You can hear that. But, right, so when this dissociates, we have 1 magnesium for every 2 hydroxides. And if you look up the Ksp value in the back of your book, this is 5.6 times 10 to the negative 12, which is equal to, and we're going to plug in x, right? X and then 2x squared. So essentially what we want to solve for, of course, is the hydroxide concentration. But in order to do that, we have to determine what x is. So this is then equal to 4x to the 3. So divide both sides by 4 and take the cube root. X ends up being, I know I'm going relatively quick on this, X ends up being 1.12 times 10 to the negative 4 moles per liter. Now keep in mind, we want the hydroxide concentration, which is really equal to 2x. So for hydroxide, it's going to be 2 times this value, which ends up being 2.24 times 10 to the negative 4. At any point in time, if you wanted to pause the video and give these a try and then see how you do on your own, that's not a problem. Okay, and of course, just continue watching if you feel like this is a good piece for you. So now we have hydroxide, so we're going to solve for our hydronium, right? So we have hydronium times hydroxide. So we have 1.0 times 10 to the negative 14 is equal to, I'm going to put in x here again, different x this time. And then once we isolate for this, right, our x value, which is now hydronium here, we end up getting, and then to 2 sig figs, oh, there's no values here, but I have my value, my answer to 2 sig figs. 4.5 times 10 to the negative 11. So those are our two. They wanted us to solve for the 2 ion concentrations. So since there's no sig fig reference, I mean, really, you could keep them both to 2. I just so happened to randomly do this. Okay. So this one's a little bit more complex because we have to do more steps at the beginning here. But let's take a look at this in the next video.